In this video, I want to cover the basics of viscoelasticity, which is the most straightforward way to begin understanding the behavior of complex materials. And they're complex in the sense that they behave both elastically as well as viscously. So they bounce, they carry a seismic wave, which are types of elastic behavior, where they will respond really quickly and return to their original shape. And then viscously means that they're flowing more like a fluid, and the deformation that happens is generally permanent. The way we begin to look at this is through a way of modeling it where we can use elements that we can describe diagrammatically. This being a spring that has some force attached to it, and a spring has what we call a spring constant in if we're talking about a real spring, but that spring constant is also more generally what would we call the elastic modulus. So we're just using this as a model for elastic behavior. We're not actually saying that there are little springs inside the material. But in this case, if we apply a certain amount of stress, or the force over the area, then we'll get a certain amount of elongation of the spring. So a specific amount of stress results in a specific amount of elongation. A larger amount of stress results in a larger amount of elongation. And for the perfect material that behaves like this is a linear relationship. And the slope of that curve is our elastic modulus, which is mu. So that's the slope of that curve. We can then write this relationship that the stress through time is equal to our elastic modulus times the strain. Or we can turn this around, that the strain through time is equal to, the stress through time over the elastic modulus. For the spring, any deformation that we get, any strain that happens, comes back to zero when we take the load off. So we always recover the deformation. And that means we also always recover the energy that we put into it. So it takes energy for us to extend the spring, and it will take energy, we'll get energy back when the spring relaxes. The other basic element that we work with is the viscous element. And we represent this as what's called a dash pot. It's like a piston or a plunger or a syringe, kind of, where we have a fluid within a bucket with a little plunger that can go back and forth. And that the behavior of this, the piston inside here responds to the behavior of the fluid. So again, this is our fluid, this is our viscous material, which is more fluid-like. And in this case, when we apply a stress, it's not dependent on, it doesn't respond with a certain amount of net deformation. It deforms at a specific rate. So a given stress, will cause it to deform at a given rate of strain. And the same thing, at a higher stress, you get a faster rate of deformation. So this linear relationship is called, the slope there is called the viscosity, which we call eta, and this viscosity for the idealized material is linear. And in that case, our relationship between stress and strain rate, we can write most simply like this, where the dot implies that time rate of change. Our net strain over time, so note this is strain, not strain rate here, is we can determine just by integrating our stress through time. In this case, because we do end up with a net strain even after our stress returns to zero, the deformation, that net strain, and the energy that we put into it are not recoverable. So this is the other basic element that we work with. We can then combine these elements to try to, and combine them both in terms of our diagrams, but also in terms of combining the equations in order to get a more complete and complex behavior. We could add a third element in there if we wanted to, and that would be an element that represents failure, which we represent typically with a block sliding on a table, for example, and the behavior, or the amount of force that allows this block to slip is the modeled way of talking about a piece of a mechanism of failure. This is not to say that all things fail in shear, because this would be a shear failure with friction defining that. So if you load it with a normal force, you might remember this from your introductory physics class, if you increase the force, the normal force on your block, you'll increase the friction, which will make it harder to fail. This is not saying that this is always the mechanism of failure. This is just one way of modeling failure. Next, I'm going to have you watch a video that shows a bit of how you can combine these together to create more complicated behavior, and then I'll come back and go through some more of the mathematics of it.